Ma'am, is it visible, ma'am?
Yes, Magita. You can start, Magita.
Yes, ma'am.
Yes.
So, good morning, all. Today we are going to see how do we interface an RTC with our 8051 microcontroller. So, we'll start with what RTC. RTC also called as and it's actually a chip is used in our PCs, laptop, and etc. And this is placed in the motherboard and has an internal battery. It has an internal battery because in the absence of external battery, we need to continuously update our time and date. So it is being provided with an internal battery, and the microcontroller is connected to this chip via externally. So since it is connected externally, we have to make a note to use the instruction move X. Since it is externally, we are using X for this. And so the chip of a real time RTC which we are using is a DS12887. This is also called as Dali semiconductor. And as I said, it is provided with an internal lithium battery because it has to work in the absence of external power. And this provides us with second, minutes, hours, days of week, date, month, year with leap year. It is also said that these informations are being uploaded in this chip up to the year 2100. Now we are living in the year 2020, and these informations are uploaded till the year 2100. And these informations can be displayed in two modes, that is in 12-hour mode and as well as in 24-hour mode. And this 24-hour mode is nothing but the time mode which we can see in railway stations. For example, if it is 4 o'clock, they'll display it as 16:00:00. So that is 24-hour mode. And we also have the option of choosing between 12-hour mode and 24-hour mode. And this thing is also called as a DS12C887. So the C here stands for CMOS because we are using CMOS technology as it helps us to keep the power consumption low. And here CMOS memory is also used because it is a non-volatile RAM. And ma'am has already explained to us about a non-volatile RAM, which is nothing but during the power cycle, our data will not be lost. It will remain as is and it will be updating itself. So the next we'll go on to the pin diagram. So this chip is actually, it consists of 24 pins, and the 24th pin is the VCC. Now this VCC is the pins which provide supplies with external voltage. External voltage should be 5 volts, and it is actually I've said that this is a non-volatile memory. So non-volatile memory means it is not affected by any voltage values. But why are we giving this 5 volts is solely for the purpose of programming to access registers. We are giving external voltage for this. Other than that, the voltage does not affect the chip in any other way because it is non-volatile. And here we have 3 conditions. That is when the VCC voltage is less than 3, and it is less than 4.25 volt, and it is greater than 4.25 volt. So when the VCC, the supplied voltage is less than 3 volt, what happens is the external source is switched on and the internal battery provides power to RTC in order to switch on the chip. And if it is less than 4.25 volt, what happens is the read and write to this chip are prevented. And if it is greater than 4.25, the device becomes accessible after 200 milliseconds. What this means is when we start this RTC, it takes 200 milliseconds time to get switched on. That is, we have to provide it with a delay of 200 milliseconds. So the next pin is the ground pin. The ground pin is the 12th pin. Next comes the AD0 to AD7. AD0 to AD7, these are multiplex address or data pins, which provides us with both address and data. This AD0 to AD7 are connected to the microcontroller port pins P01 to P07. It is like AD0 is connected to P0.0 and AD1 is connected to P0.1. So it is connected like that. And the addresses are latched on the chip and we'll be seeing out another pin called as AS. During the falling edge, that is falling edge is nothing but high to low transition, the addresses will get latched on these AD0 to AD7 pins. And as I said in the first slide, we have to use the opcode move X because the chip is externally connected to the 8051. So in the picture, we can also see how 8051 is connected with the chip. ALE is connected to the AS, the right pin to the right pin of the chip, the read pin to the read pin of the chip, and the P0 connections, port connections also we can see. So the next we are going to is AS. The AS is the 14th pin, and this AS is also called as address drop. And this is the input pin. That is when that is of when there happens to be a transition from high to low. The address and data it will latch the address and data into the AD0 to AD7 pins, and it is connected to the ALE of the microcontroller. As we know, ALE also is called as address latch enable. And the second one is MOT, and MOT is the first pin, and this is actually an input pin. And in earlier days, there used to be two bus timings, that is Motorola and Intel. But nowadays, we are using only Intel. To select this Intel timing, we have to make MOT equal to ground. In other words, I can say that if MOT is equal to ground, we have selected the Intel timing and not the Motorola timing. And the next one is the DS, and DS is the 17th pin. So DS is also called as a data stop or read. This is also an input pin. When MOT is equal to ground, we can say that DS is called as a read signal. So this read pin is connected to the read pin of the 8051. And the next is the read and write pin. So this one is the 15th pin. And if MOT is equal to ground, we can call this as write signal. And this is connected to the right pin of the 8051 of our 8051. And the next comes our CS pin. The CS pin is the 13th pin, and this CS is also called as chip select, and this is an input pin, and this is called as active low signal. So what is called as active low signal is that when the signal can work only when it is in its low state. That is, when it is in its zero state, the signal can work. And during this read and write cycle, CS must be low to access the chip. And this CS can work only when external VCC is connected. So there is also an extra state here, which is called as write protected state. So what happens in this write protected state is that all inputs will be ignored because they will reach an inactive level. So when will this inactive level be reached is that when VCC is less than 4.25 volt. So when VCC is less than 4.25 volt, all inputs will be ignored. But when VCC is greater than 4.25 volts, we are able to on our chip and access it. So the next comes IRQ. IRQ is nothing but the interrupt request, and it is an output pin, and it is also an active low signal, which means it can only work when the signal is low, that is its state is low. And to enable this interrupt request thing, we have various interrupt enable pins in register B, which we will be seeing in the upcoming slides. So if we enable those pins, we can also enable this IRQ. And next is the square wave. So this square wave is the 23rd pin, and this square wave is an output pin, and it is said that we can generate square waves from this pin, and this frequency can also be selected by us. It is said that we can provide like 15 different square waves out of this pin. And the last comes the reset. It is also an active low pin, and it is an input pin. It is connected to the VCC. If this reset pin is low, what we can do is we can reset our IQR. That is, we can reset our IRQ interrupt request, and we can clear the SQW, that is the square wave pin. And this reset, it does not affect the clock calendar and the RAM informations that we have. And the next we have come and the next is address map of the chip. So this contains of 128 bytes of RAM space with address locations of 0020 and here we can access all those 128 bytes to read and write data, although there are some exceptions. That is, here we can see in the diagram there are 4 registers A, B, C, D. The exception is that in the entire 120, we have said that in the entire 128 bytes, all bytes can be used to read and write data, but this register C and D are declared as read only, and the 7th pin of register A is also read only. So these are some exceptions for the case. And the high order bit of the second byte is read only, and these are the 3 exceptions. So if we see from address location 00 to 09, we can see that it consists of seconds. Seconds are minutes, minutes are hours, hours alarm, day of the weeks, month, year, and everything. So these 00 to 09 is used for fixing our is used for RTC purpose. That is to fix our time, date, and etc. And from 10 to 13, we in 10 to 13 consists of the control and status registers, which are nothing but register A, B, C, and D. So we know that this chip is going to have an oscillator. So how are we going to on this oscillator? So initially this oscillator is being kept off in order to save our lithium battery. So in order to switch the oscillator, first let us have a basic idea on the bits of a register A. So in this diagram, we have a bits of register A. That is, we'll start from D0. So D0, D1, D2, and D3 consists of bits RS0, RS1, RS2, and RS3. These bits are responsible for providing different frequencies for our square wave pin, and it is said that it can produce up to 4 different frequencies. And after that, we have DV0, DV1, and DV2. These bits are very important because this is what is going to turn on the oscillator. So whenever we write the program to turn on the oscillator, we have to make sure that we set this DV1 to 1. So this so that's all. And the last D7 is UIP. We have seen in the previous slide that D7th bit of register A will be read only. And so here we are going to use, if the address is in 8 bits, we can use R0, and if the address is in 16 bits, we are going to use DPTR. And so this is the basic programming to turn on the oscillator. So as we said, we are providing it with voltage greater than 4.25 volts. So normally we have to initialize a delay of 200 microseconds. So we are calling a delay of 200 microseconds, and then we are using move R0, #01, which is nothing but here we are using direct addressing mode. We are pointing it to address 01, which is nothing but the address of register A. And in register A, we have to turn on DV0, DV1, and DV2. So in order to turn on, we will write it as 010. So if you write it in hex format, we will get hashtag 20, hash 20h. And after that, we are going to use movex at r0 comma a. This is nothing but here we are using indirect addressing mode. What we do in indirect addressing mode is that the value from accumulator a is being loaded into the location pointed by the r0 register. So the location pointed by the address pointed by the r0 register is 01, which is in a register. So we are sending the value of 20h to address A so that our oscillator gets turned on. So next is two basic programs, like how we are going to set the time and how we are going to set the date. So first thing is we are going to set the time as 16:58:55. As you can see, this is in our 24 time mode. So first, as we saw on the earlier slide, we are initializing a delay of 200 milliseconds, and then the previous program we've again written, like turning on the RTC, and then we are coming to set the time mode. So for setting the time mode, we have to use register B. Here you can see that D1 is 24 by 12. So if this 24, if this bit should be set to 1 if you are using the 24-hour mode, and this bit should be 0 if you are using the 12-hour mode. So DAC is nothing but daylight saving enable. This is generally one for everything. And so we are initializing, and then we have here set, and this set bit is always 1. This will inhibit or update, that is after during initialization you shouldn't update the time and clock. So for this purpose, we are setting it to 1 to inhibit the update. So whenever we are initializing this B register, the set bit should be 1. The set bit should be 1. So that is what we are doing here. That is why we are writing hash 83, and we are sending this hash 83 value to the B register address. So we have set the time. So we have done with the time mode, and next we are going to come to the setting time. So this is also the same. What we have to do is first we have to start with the second part. We have to take the we have to first initialize the second address. The second address is hash 0. So after so first we have to point the address location of our second, and then we have to initialize our we have to give in our data value, that is 55, and this 55 is stored in the second register address. So the same we are following it to minute address. Here the minute address is hash 02, and we are giving 58, and we are storing 58 in this address, in minute address. And then last is 16, which is the R mode. The address is 04. So we are taking the value and storing it in our R address register location. So the same comes to setting the date. So you can follow the same procedure of like a call delay 200 milliseconds, and turning on the RTC program is also the same, and setting time mode is also the same. And then we are coming to setting the date, which is also the same method. But here the only thing that changes is the register address. For day of month, for day of month, we are using 7. 7 is the address, register address for day of month. And then we are initializing the day of month as a 19, and then we are moving it into the register. And then again we are calling a delay. And for month, it is address is 08. And then October, since it is the values are predefined in this chip, if you give 10, it is enough, because October is the 10th month of the year. For example, if you want to give July, if we put 7, that is enough. And again, we are sending it to the register address, and we are calling a delay. And for year, the address is 09. And after that, we are putting the value is already since we are in the 20th century, the 20th era, 20 is already pre-installed there. You have to give only the last 2 bits. If it's for 2004, we give 04. And if it's for 2020, if we give 20, that is enough. And again, we are storing it in the register address of the year, and we are calling the delay. So this is the basic program. And so the next program is for setting, reading, displaying time and date. So here, we already know our like how do we write our C programming here. So first we'll use the header file, that is reg51.h, and the second we have used the header file, that is absacc .h. So why is this header file used is, like we already know we are using move x instruction here because we are obtaining data from an external memory source. So we are using here x byte. So this x like it defines that it is external. So when we use x byte, we have to make sure that we use the header file absacc.h. So as usual, we are going to the main program. We are generating the delay, and in the x byte, we are going to initialize we are initializing the address. This is for turning on the oscillator. We put this in this 10. It denotes register A's address, and then we are putting it as into 20. So we are using here 0 into x. So why we are using x is to indicate that it is an hexadecimal number. So we know that 010 only we are writing it as 80, and the same procedure goes for b for writing the B register address 11 and to set the timer mode. And then this 024 is nothing but the second, minute, hour register number, and we are putting our initial values here. And the same goes for day, month, year, and we are going to allow the update. And here we are going into our main program. And to display this, we have to convert our BCD to ACC in this program. So first thing is we are initializing with unsigned char as character, and we are using t mod 0 into 20, which in t mod into 20, and this is the second thing is baud. We are giving the baud rate value, and then and then we are going for the SCON, and then we are using the timer 1 because we know if it is 0 into 20, we can say that it is timer 1 mode 2. And after that we are going into the while loop, and here it is we are transferring this we are transferring our inputs into the variable r, and we are sending it into and like we are sending this r value into our variable, and minute value into minute variable, and in between we are and in between we are displaying this colon also, because that is how we denote our time. So these things is going to get converted into the into the ASCII form. So to convert this ASCII form, what we do is we AND it and then we OR it. This is to separate the bits into lower bits and higher bits, mask it, and then we are going to use a right shift operator. And after this, after we get the information from that, we are sending it to like serial we have already like we already know about serial communication. And here the values are stored into the S buffer, that S buff. And then this is transmit. We already know this is a transmit flag. And this part after this, after we after this we are initializing the transmit interrupt to 0. So this is the basic program, and this is we have seen for time. And if you want to do it for date, the same it also follows the same procedure. And so this is a register B and C with some of its major bits. We have already seen about some of the bits of register B. And so we have the extra one here is PIE. PIE is nothing but periodic interrupt enable, and UIE is nothing but it is AIE is nothing but alarm interrupt enable. So we'll be seeing about this later. And this is the register C. And okay, so in register C we have this AF. AF is nothing but our alarm. So AF is also called as a alarm interrupt flag. When this alarm interrupt flag is equals to 1, we can say that the real time and the alarm time which we set is equal is same. For example, if I set my alarm to 4 o'clock in the evening, and if the real time is also 4 o'clock, then this AF will become 1, and this and if this AF is equal and if this AF is equals to 1, then AIE will also be equal to 1. This AIE, this is nothing but alarm interrupt enable AIE. So this AIE, we have seen this in register B. So this, if AIE is also equal to 1, then our interrupt request it will be low. That is the 3 bytes, that is the hour, minute, and seconds of our alarm time, and the real time will be same. And this AF can be will become 1. This interrupt can be established once per second, once per minute, or once per hour. This is the alarm and square features of this chip. And we have already seen that SQW provides a square wave output at various frequencies, and we can see in this table that we have various frequencies, that is, I think, 15 to 14 frequencies we'll be having. So this is how you will, and this program here is how you will choose the frequency. So this goes the same. Like the first we have selecting register A's address, and here we are turning on the oscillator, so that we will write as 010. That is nothing but 20. We got that 20H. But here the thing is, here DV1 will be 1, plus you have to set the bits of RS3, RS2, RS1, and RS0 to the frequency you are selecting. Here we have selected 4 hertz of square wave. So here it is 444. I mean, it's 111. At RS1 it is 1, RS2 it is 1, and RS3 it is also 1. So we are getting hash 2EH. And after this value, we are initializing this value to the we are loading this value into the register A, and the same goes for register, and then we are selecting register B. And here what we are doing is, we are the value of R0, that is, we are getting the register B of this chip, and we are storing its location in our accumulator. And again we are calling the delay, and in order to get output of the square wave, we have to use this instruction, that is nothing but set bit ACC 0.3. This ACC is nothing but our accumulator, and again this value of A, we are sending it back to our register B. So this is the basic program. And we have already seen this, that is, the alarm interrupt can be programmed to occur at rates of once per day, and once per hour, once per minute, and once per second. So how do we get an interrupt like once per day is, first we have to select write the desired time for our alarm. So for example, if I want to set my alarm at 4 hours, 4 hours 5 minutes and 10 seconds, in like, if it is like one is the alarm second address of address, and so in the register address of 01, I have to initialize my second value. If it is 10 seconds for me, I have to initialize 10 in this address location 1, and the same goes for minute and hours. And however, we have to make a note here that the registers which we use to set our alarm time is different from the registers we use to initialize normal timing. Okay, so if you take a look at the diagram, you will see that there are different register locations for both. And when the real time matches our alarm clock values, our alarm interrupt flag will go to 1, and we have to enable our ALE flag, which is in register B, to also 1. And For enabling an interrupt at once per hour, we have to write FFH into alarm hour location. That is nothing but at the location 05, we have to write FFH. And for once per minute, we have to initialize FF at both locations. That is at R also, at R location, location also we have to initialize FF. And for minute location also we have to initialize FF. And for second, we have to initialize FF at all three register locations. That is at register location alarm R, register location alarm minute, and at register location second, we have to initialize. That's we have to store the data FFH. So this is the connection diagram. How we are using the square wave to sound a buzzer. Here, just make a note that we are using an AND gate. It will this AND gate we will be using it while we program. So you have to make a note of that. And the next thing is interrupt. The next is our IRQ feature. IRQ is nothing but our interrupt request, and this IRQ is also called as an output pin. It is an output pin, and this IRQ can be enabled by three ways. That is by alarm interrupt, periodic pulse interrupt, and update interrupt. This alarm interrupt is when the ALE flag is set to high. So that is we are using our ALE bit in register B of our chip. So these are the three ways on how you can enable your IRQ. So this is how you so this is the diagram on how you activate an interrupt by using an IRQ. Make a note here that IRQ is connected to the external timer of INTO. This int 0, int not. This we have already seen in our timer chapter. And so this is the last slide. This is an example of a program. That is what we are going to do is we are going to send a message called S to the serial port once per minute at exactly 8 seconds past the minute. And we are going to and the buzzer we are going to turn it on and off after for 7 seconds before it is turned off. So let us see this program. So first one is we already know because we've seen it in all our previous chapters and also in our lab experiments, serial port communication and timer mode programming. So first we are writing as origin 0 and long jump me. We are using this long jump in order to skip the interrupt service routine, and we are going to the main loop. And here we have enabled our interrupt enabled to #81#. We know that since we are using external timer 0, we use the #81#. And then we say that here in order to produce this delay and transfer the signal, we have to initialize an edge trigger. So that is why we are setting this set B as tcon 0.1. And after that, we are selecting timer 1 mode 2 and then the SCON register. And then we are initializing our baud rate. It is 9600, which is -3, into our flag, and then we are going to set a bit, and we're going to start our timer 1. And these programs we have already seen in the previous slides. So you have to write the code for turning on the RTC mode, and then again you have to write for setting the timer mode, and then again you have to write the program for setting your time. So after this, what you should do is just as how you set the time, you have to set the alarm time also. So you can see the same steps repeating again and again. Only the register values will be changed. That is 1, 3, and 5. And what we are going to do is here, since it is 8 seconds past minute, we are initializing the value as 8 into our alarm second register location. And then once per, we have already seen if it is once per minute, we have to initialize 0 FF. And if it is once per hour, we have to initialize 0 FF. And after initializing this, we are calling a delay, and then we are selecting our register B address. And however, it is important to note here that we are using here as move a hash 23h. The sole reason why we are using 23h is that in register B we are initializing D7 to 0, which we have already seen, because we have to store that's for the update. And then here we are setting our AIE bit to 1. So so here we are setting this AIE bit to 1, and this set we are initializing it to 0. So this is why we have written here as 23h, and after this we are moving this value 23h into our register B, and then we are including a code which we used it for reading time. We have seen in that program, that big program. So how to initialize this reading time. And then comes our serial transfer. Yeah, so here what, so always in a previous program we used to always set this IE to 7, that is external interrupt. We always used to set this, but why are we clearing it here, or why are we disabling it here, is that because this external interrupt should not get confused with our transmit interrupt. So that is the reason why we are disabling the interrupt as the first step. And then we are moving our A value into the SBUF, and then we are monitoring our transmit flag. And after it is completed, we are clearing it and getting it and keeping it ready for the next transmit to occur. And as you can see, once the transmit flag completes its role, we are again setting our external interrupt to 1, and then we are returning to the main program. So the next is our interrupt service routine, and here we have to send our value yes. So here you can see that we use in the first part of the code we are using 03, because we already know that because we're using timer 0 external timer 0, we're using this 03 address location. And after this here we have and if we come to the interrupt service routine, we here we are we are initializing our register C, we are calling the delay, and again we are moving the data into our register C, and the same thing we are following it to register B. And after this from this set B ACC point 3 we've already seen, this is to get the output from the a square pin. And this we are going to set this P7.7. So this P7.7, and here you can see that P7.7 and this SQ are in AND are connected to the AND gate, and that AND gate is in turn connected to the buffer. And after that we are putting the value of Y, and we are sending it to the serial port, and then we are transmitting the value. So it follows for YES, and after everything we are again storing this in our registered C's address. And after that what we do is we will clear the P1.7 port, and we will return our interrupt. So the main things we have to note from this program is that we have to first enable the external hardware interrupt to make it edge triggered. So that is one thing we have to make a note. And the second thing is AIE should always be set to high. The main reason why we are setting this AIE to high is to I think I forgot to mention here. If AIE is 1 only, then our IRQ can be low. So why is this IRQ should be low? Is that since it runs on BIOS setting, that is basic input output system, we have that is nothing but hardware initialization during booting process, right? So for that reason our IRQ should be low, and in order to keep that IRQ low only, we are setting this AIE pin to high. And after that We have to also be careful of disabling the external interrupt and again enabling it. And yeah, so that's all. Thank you, everyone.
Nagita,
Ma'am?
thank you, ma. That was a good presentation.
Yes, ma'am. Thank you, ma'am.
Students, do you have doubts regarding this real-time controllers, real-time clock?